Okay, so it's not working. Oh, there we go. There we go. Okay, so last time we talked about a priori. I gave you an example of Babe Ruth, that he became famous by pointing where the ball was going to go, right? Remember, he points in a certain direction, he hits the ball, baseball, hits the ball goes exactly where he pointed. Very, very impressive feat. He became very famous as a result of that, and so on. So what did he do? He did two things. Number one, he pointed. Number two, he hit the ball, right? Got it? Two things. What if I reverse the order? First he hits the ball and then he points. Doesn't mean anything, right? So you see the same actions, the same two actions exactly, and if you reverse the order, all of a sudden it's meaningless. Doesn't mean a thing. He pointed it, okay, he saw where the ball went, so he pointed, right? So now we're going to go a little bit deeper into a priori and why it's important in terms of the Torah codes. When you can sort of get around it a little bit, we'll see an example of that. And the calculation of probabilities basically is, how do you know? Because you see, a lot of people will say, well, the Torah is a very long document. Okay? It's hundreds of thousands of letters long. How do we know that, take any document, you look far and far wide enough, you're going to find whatever you look for almost, if it's long enough. How do you know that this doesn't just happen by chance? And we're going to discuss that, and that's what's going to make the difference between a real code and what we call a counterfeit code. Now, the question is, why are there counterfeit codes? Two reasons, and they're exactly the same reasons as why there's counterfeit money. Reason number one, people want to have money and they don't have the money, so they'll counterfeit money so they can have money, right? That's one. That represents the Christians, who have also done this kind of thing, but they come up with codes that look perfectly legitimate, but if you don't know how to evaluate them, the looks is deceiving. You look at a counterfeit bill. I wouldn't know what's a counterfeit 20. I don't know if any of you would. You have to have a special pen that you put on it, right? And it comes of a different color if it's real, and then there's other ways to look at it. You have to have a chachma to understand how do you look at this to make sure that it's real. And it's the same thing with the codes. The other reason is during warfare, for example. What you do is you fly a plane over the enemy territory, hope it comes back, of course, and you release tens of thousands or hundreds of thousands of counterfeit bills. You devalue the currency. And therefore no one knows what's real, what's not real, and it affects their economy, and anything that you can do against them is going to help the war effort. And that's the same thing over here with the critics. They're not trying to prove anything. What they're trying to say is the codes are not real. So we'll show you we can get codes in War and Peace, for example, or in Moby Dick. And they'll produce things that look perfectly legitimate. But as soon as you apply the tests, and I'm going to show you how to, not the details of how to do it, but the idea, you suddenly see that there's a world of difference between a counterfeit one and a real one. Okay? So I used to be, I don't know if it's still true, with an American dollar, it had like a place with like a circle with a lot of little triangles around the edges of it, right? You remember that? Remember that? Like little spikes coming out of it. Well, if you looked at it under a powerful magnifying glass, what you would find is that for a real bill, the spikes were really sharp and precise. For a counterfeit, it was usually fuzzy. They couldn't produce something that was quite that fine. That was one way of looking at it, but the same thing over here. Okay. So the first thing that we have to know is that probability, although I've been talking about probability, or odds as you might call them, is really, really not what we're interested in. Most of the time, it's going to work, but it's really not what we're interested in. What we're interested in is something called the expectation. So, the question that we're going to pose is, if you see a code, the question is, I don't care what the probability is. Did you expect to find that code in the Torah? Okay, think of it, right? If you expected to find it, and any document that long, it's meaningless. It means that, yeah, this kind of thing just shows up by itself. If you didn't expect to find it, the question is, well, how much didn't you expect to find it? So you get an expectation. How many times do I expect to find it? If it's one, it means that in the Torah, for example, you expect to find it once, just by chance. In any book that size and with the same kind of letter distribution and so on like the Torah has, you expect to find it once. If it's 1/10, that means you'd have to try it on 10 different documents the size of the Torah before you expect to find it once. So now it's beginning to say, well, okay, but maybe we're lucky, but it's not so obvious. If it's 1 in 1,000, you say, wow, that's something you really didn't expect to find that. So let's take a look at some very, very simple examples. So we said that in order for an ELS to be called a code, right? So number one, it has to be an ELS. It has to be an equidistant letter sequence, right? So equally spaced letters in a certain same distance between the first letter to the second to the third to the fourth, and so on. Number two, it has to have something about it which is unexpected. Notice it's underlined. You don't expect to see it. So when you do see it, it's a surprise. You say, wait a minute, there's something funny going on here because you don't expect to see that, and yet you do. Okay, that's the idea. Now, let's take a look at what the expected really is. Take a look at the first thing that has the red box around it, okay? Right above it, the expectation is equal to the probability times the number of trials. Now we'll give an example. We'll see in a minute, but I'll just tell it to you orally first. And that is, imagine that there's a lottery tickets that are being sold. 1 million people buy the lottery ticket, okay? There's a 1 in a million chance of winning. Someone wins. Are you surprised? It's a 1 in a million shot. But after all, there are 1 million people buying. So you expect one person to win because it's the product. You multiply 1 million times 1 in a million, you get 1. You expect one person to win. Okay? Now, take flipping a coin. That's right over here. If you flip a coin once, you have the expectation of getting a heads is a half. Which means that every 2 times you flip a coin, you expect to get 1 heads. Now that's an average. Doesn't mean you're going to get it the very first time you flip the coin twice. But on the average, as you go more and more and more, you'll find that you're getting 1 heads for every 2 flips. Right? Makes sense, right? So the expectation is a half. If you do 2 flips, it's going to be a half times 2 is equal to 1. You flip the coin twice, you expectation to see your heads once. Okay? Now, there's a very deep concept over here. This is very simple, but listen. If I say something is a priori, that means I define it beforehand. If I define it beforehand, that means the number of trials is 1. I'm doing this trial and no others. So, example, with the coin, I'm going to get a heads on the first flip. That's a priori. I'm not telling you that of all the flips, somewhere it's going to be a heads. No, I'm going to flip the coin now, and this particular flip is going to come out heads. Now the expectation is, because the number of trials is 1, the expectation is the probability of getting a heads, which is a half, times 1, which is a half. So when you have a priori, the number of trials is always 1, and the probability equals the expectation, which is why in most cases you can talk about probability instead of expectation. This comes in very clearly when you have more than 1 trial. We'll deal with that in just a moment. Again, well, let's just go on and we'll see how it works. Okay? So does everyone understand what I'm saying? Right? Okay. So, wrong one. Okay. So here we have, say, 1 million people. I challenge anyone to count it and prove I'm wrong. Anyway, you have 1 million people, right? Lottery tickets. Probability of winning is 1 in a million. The expected number of wins is 1 million times 1 over 1 million, which is 1 million over 1 million is equal to 1. If somebody wins, somebody, unspecified, just someone of those million, where somebody wins, it's no surprise. Now, if I specify 1 person, I say, he's the guy who's going to win, it's now a priori. If he wins, it's a big surprise. And what you're going to probably do is say, I'm going to investigate how this lottery is done. Because someone shouldn't be able to predict. That's unexpected. In fact, the expectation is exactly 1 in a million. Right? Because the number of trials is 1, the probability is 1 in a million, so you multiply them, the expectation is 1 in a million. You're going to say, something is going on here. Investigation is called for. Everyone with me? Okay, now let's take a slightly more complicated example. what happens if I know that only 5 people bought lottery tickets? Now, the expectation is going to be 5 over a million. The number of trials is 5, right? And the probability is 1 in a million, so it's going to be 5 times 1 over a million, which is 5 over a million. Now, that's not as good as 1 in a million. So if someone of those 5 wins, well, 5 out of a million is still going to be a big surprise, but not quite as big a surprise as 1 out of a million. Everyone with me? Mm-hmm. Okay, because now you have 5 people that could have won. The more chances for someone to win, the greater the expectation that one of those people will win. Obviously, if you expand it to 1 million people, the expectation is that one person will win it. Now, what happens, and this is very important, what happens if you don't know how many people bought lottery tickets? Now, I say the probability is 1 in a million. It sounds great, 1 in a million. But remember, the probability doesn't count. It's the expectation that counts. And the expectation is going to be the number of trials times the probability. I know the probability is 1 in a million, but I don't know the number of trials. And I can't multiply something I don't know, so that at the end the expectation is a big question mark. You don't know. And that's the correct mathematical answer. If you don't know the number of trials, then you don't know and you cannot calculate the expectation. Now this is the problem with someone who does a code and tells you, this is what I found, it has a probability of 1 in a million, but he doesn't tell you how many trials he did. There's no way to evaluate it mathematically and know that what the expectation is. You don't know if it's good or not. If the number of trials is big enough, it'll overwhelm any probability, no matter how small it is. Everyone with me? Great, you're doing great. Now, before we said there were 5 people. Now, sometimes it may be possible, we're going to discuss this later, sometimes it may be possible to have an estimate of how many people probably bought lottery tickets, for example. In which case, you could get an estimate of the expectation, but not an exact number. If you don't know the exact number, you can't do the multiplication. But if you know that no more than, I'm sure there were no more than 100 people who bought lottery tickets, okay, then you could say that the probability, the expectation is going to be no more than, is going to be no less rather than 100 divided by a million. Now, how do we evaluate the Torah Codes? The fact of the matter is that the ultimate way that you really like to be able to evaluate it, first of all, assuming that you know the number of trials, because you're doing the experiment, so you know how many things you've tried. So now the question is, what's the probability? And what you'd like is some kind of a mathematical formula that you just plug in all the variables of what you've done, and out comes the probability. Unfortunately, it's not possible. And the reason it's not possible is that the Torah, in the case of the Torah, is that the Torah is not a random text. The Torah has grammatical structure to it. And as soon as you have all kinds of structure that you don't know how to precisely define mathematically, you are in trouble. Because the calculation goes out the window. Expectation, you know what the expectation is. I'll give you a very simple example. What's the probability of seeing lightning during the winter time? I don't know what it is, but let's just assume it's 1 in 200, for example, right? 1 in 200. What's the probability of seeing lightning if you hear thunder first? Well, it's the other way around, I guess. First you see the lightning, then you hear the thunder, right? Okay, so you hear the thunder 1 in 200. What's the probability of seeing lightning afterward? Well, you know, it's going to depend. If you hear the thunder first, there's a much higher probability that you're going to see the lightning afterward than if you didn't hear any thunder. So the two are connected. And as soon as they're connected, the probabilities go out the window. You have to actually do a study for each one individually. And that's what they do over here, because of the grammatical structure of the Torah. So the critics say, but you're assuming it's an ordinary document, that of course there are all kinds of, it's a language, and therefore everything goes out. We understand that. We've taken care of that. But remember that. What do? There are several ways of doing it. The first way is that we randomize the texts. Okay, so you take the Torah, and what you're going to do is you're going to mix it up some way. Now, why are you going to take the Torah rather than random stuff? Because you want to preserve as much as possible of the way the Torah is, to get an idea of what happens when it looks like the Torah, but it's not the Torah. Okay? So one way is to simply mix up all the words within each sentence. And that way you preserve the word structure. So anything letters that go together, like in English, the Q is always followed by a U. There are similar things in Hebrew, but a little bit more complicated. You're going to preserve that. Furthermore, where the letters occur, they're going to occur approximately where they did before. They're not going to be moved all the way to the other end of the Torah. It's going to be within one verse, and so on. So that's one way. Another way is mix up the sentences. The other way is mixing up the chapters. Now, of course, mixing up the chapters, there's a problem here, and that is, yes, it's not the Torah, but the problem is that if it looks too much like the Torah, you may get results anyway, even though it's not the Torah. So any code that's contained within a chapter, which is pretty big, is going to be preserved. So you have to sort of take a balance of, yes, it's not the Torah, but it's not too much like it. It resembles the Torah, it's not too much like the Torah. The one that we basically picked is mixing up the words in each sentence. So, for example, that sentence that you had above in there is now somewhat mixed up. And you can do this in as many ways as you like. Trillions of ways, actually. Not for a short sentence like this, but if you have a whole Torah, each sentence, you can mix up so many of them. And then what you do is you take a look and see this code that I found. How often do I find it in all of these? They call them monkey texts. Because the question is, how long would it take if you had an army of monkeys typing randomly on a computer or a typewriter, and how long would it take before they produce one of the Shakespearean sonnets or something like that, right? They actually tried the experiment, by the way, and it just failed right away, because what the monkeys did, they didn't type on the keyboards. What they did is they peed on them. But aside, that's a true story, by the way. But aside from that, so what we're going to do is we're going to mix up the words, and we're going to see how many times, if I mix it up 1,000 times, and I don't find it at all, except for the real one, which is not mixed up, I know that the probability is probably around 1 in 1,000 or less. I mix it up 10,000 times, I find it once, 2 times, then it's 1 in 5,000 or 1 in 10,000. Okay? Just by trying it. See, how often does it happen? No mathematical formulas. Whatever structure is in the Torah, it's almost perfectly preserved over here. So if it happens, if you do it 1,000,000 times and you mix up text, then the expectation is going to be, if you find it once, it's going to be 1 in 1,000,000. Okay, so with that background, let's take a look at the Great Rabbi's experiment and the controversy. Yes?
Sorry, I must have missed this, but what codes specifically are we looking for? Like what kind of code?
Okay, what we're looking for is codes, words that are equally spaced, equidistant letter sequences, which means that you take a look at a letter, you have a word, you look for it in the Torah, such that you find the first letter, you find the second letter, let's say 7 steps, 7 letters away, ignoring the spaces, then you find the next letter of the word again 7, again 7, again 7, until the last letter of the word. So that's called an equidistant letter sequence. It's a sequence of letters which are equidistant from each other. Okay, it could be 7, it could be 1,000, it could be 1,013, whatever. So long as the distance from the first to the second letter is the same as the distance from the second to the third to the fourth to the fifth, until the end of either the word or the phrase, as the case may be.
So it's any.
And now what you're doing is you're finding what's called compact configurations. You take 2 words, like, for example, my first name and my last name, Harold and Gans, and lo and behold, you look for both of them and you find them, which is nothing unexpected. You expect it. So long enough, 4,805 letters in the Torah, you expect to find, put it in Hebrew, Harold Gans, you're going to find it. But you don't expect necessarily to find them very close together. And that's the effect that we're finding. Okay? So we had a whole bunch of examples last time. I'm sorry you weren't here, but that's the basic understanding. So we're looking at a configuration, and what's unexpected is how compact that configuration is. I can produce a chart in which you'll see both words near each other on that chart.
I mean, the smaller the letter skip, the more impressive.
That's an easy question with a very complicated answer. There's some indication that if the skips are smaller than you expect them to be, then yes, it is more unexpected. But that's a slightly different effect. What we're dealing with over here is that we're not dealing with what is the skip. It's just a matter of, at this skip, for this word, at this skip, for this word, lo and behold, you can produce them so that they fit on a screen, for example.
Who is it hidden from?
Excuse me?
Who are the codes hidden from?
I never said it was hidden from anybody. So your question doesn't apply.
Why would there be a code if it's not hidden?
Ah, is it not possible for you to produce a code that you want someone to find?
Why would it need it to be found? Why is it not obvious?
Okay, so what you're asking is a motivation of the author of the code.
Yeah.
I cannot answer that. I'm a mathematician. I'm not a rabbi, I'm not a prophet.
Oh, you have thought about it.
Of course I've thought about it.
What is your answer?
I didn't have an answer. I asked a rabbi, okay? And quite an important rabbi. And what he said was, the fact that you're finding these codes, that's just, not that it wasn't meant to be found. What you're finding is, what is this document called the Torah? What is it really? It's not simply a story. It's not simply a bunch of letters. It's not simply an account of something. It's a blueprint for the whole universe. It's a blueprint for all of history. Everything is in there. It's not a human document. This was his answer. Okay? We'll get more into that as we go on, especially at the end. Okay.
And so, sorry, one more thing. So when you're scanning the Torah for codes, are you matching every letter in the Torah against some bank of predefined words, or is it every?
That's what you should be doing.
Okay.
That's exactly what you should be doing. Some people don't do that. What you could do is you could start off with one word, okay? And then you pick a second word before you start. You say, this is how many times I'm going to look for it at these skips, the distances between each of the letters. You define everything beforehand. You say, this is how I'm going to measure how close they are. This is how I'm going to calculate the probability. And when it's all said and done, and it's all predefined beforehand, I then run the experiment, and this is what success is. If it meets this criterion, it's success. If it doesn't meet that criterion, it's not success. I run the experiment. There's no question afterward. There's no if or buts. There's no, well, maybe it did. Yeah, it's pretty close, not pretty. No. Either it met the criterion or it didn't. Yes, no. Black and white. That's the way it should be done. The researchers who understand these things do it that way. But then there are people who pick one word and they look for it, and then they start looking around and say, oh, look at that, here's another word. That's not a priori anymore. The first word was a priori, the second word was a posteriori. You defined it afterward. So now you've got a question. How many tests did he really do? Right? In order to calculate the expectation. When he started looking around, how many places might he have found that word? How far did he look? If you don't know that, you can't calculate whether it's a true code or not. No matter how nice it looks, no matter how impressive it looks, from the mathematical point of view, you don't know. And that's the correct answer. I don't know. It's not calculable. I cannot evaluate it. It could either be garbage or it could be real. There's no way to know. Now, even if you ask the guy who did the experiment and you say, how did you do this? And he tells you, okay, then the question is, but do I believe him? Okay, now, I will tell you that there are certain Torah Codes researchers that I believe for myself. In other words, if they tell me they've done something, they found something, I know they're reliable, I will believe it. But I don't believe it enough to tell someone else. Until I check it out myself, and then I say, okay, I checked it, that's what it is. And in fact, last time I gave you an example of a code that had to do with the Fukushima Daiichi atomic nuclear meltdown after a tsunami. And I told you it was found by Professor Harold. He gives a probability. I think the probability he gave a probability that was about, I don't know, it might have been 1 in 15,000. I recalculated it as 1 in 6,000, which is still significant. What was the difference? The difference was he didn't tell me how many words he looked for. So he found Japan. Okay, he found the date. That's great. That's what I would have looked for. But I would have looked for Fukushima too. He didn't look for it. Maybe he did look for it. I don't know. He probably looked for it. I mean, how can he not look for Fukushima? He probably didn't find it. But I've got to count that it's one of the trials, and he didn't. Okay? Then there's also Daiichi, the Daiichi reactor. It wasn't in the code, but he probably looked for it. Another strong strike against him. So now what I did was I kept on multiplying the probability by the number of things that he might have tried until I came up with the probability. Say, okay, I think I've included all the words that any reasonable person could think of that might have been searched for. This is what the probability I believe that I can tell people, not his.
This is the probability of what?
The probability of that code appearing in the Torah as opposed to just becoming extremely random.
You're saying that someone found code talking about Fukushima.
Yeah, but we're not going to get into that.
Okay.
That was last week, and it's not relevant to today. Right?
Okay.
For this last week, too bad. I'm sorry.
Okay, got it.
But I can't go through the whole lecture of last week.
Fair.
Okay. So, this is the structure of WRR, of the great rabbi's experiment, in which this is the very first scientific experiment that was ever done by Doron Witztum and Eliyahu Rips. It's called WRR because the last R stands for Rosenberg, who was the programmer. Doron Witztum was a physics student at the time, and Eliyahu Rips is a full professor of mathematics at the Hebrew University, and a world-renowned algebraist. Published many, many papers in the field of algebra. Okay, so what did they do? They started with an encyclopedia of great men of Israel. Okay? And by the way, I went through this encyclopedia, all the places they took the names from, personally. I did it, together with someone else who's better at Hebrew than I am. Okay, so you start with the encyclopedia. Now, the question is, you want to take the personalities out of this encyclopedia, so it's a priori. If you just use one name, someone will say, well, why didn't you use that name? Well, you say, I took an encyclopedia, I took all the names. That's it. That's clearly a priori, right? The only problem is there's too many of them. So you say, well, I want the important ones. Okay, well, what's important? Important is a subjective term. You want something that's objective. So what they said is, okay, we're going to take all of the names that have at least 3 columns of text written about them in the encyclopedia. Okay? And we come up with, I don't remember the exact number, but I think it was, if I remember correctly, I think in the end it turned out to be something like 157 names. Okay? It was somewhere between 150 and 160, but I think it was 157 names. Okay, fine. Now, not only the names, but you also want their appellations, because a lot of these rabbis are better known by their appellations than by their names themselves. For example, how many people know who Rabbi Eliyahu ben Shalom Zalman is? But you probably all heard of the Vilna Gaon, right? But that's the same person. He's known as the Vilna Gaon. He's not known by his own name. And similarly, how many people who know who Rabbi Moshe ben Maimon is? He's the Rambam, but he's known as the Rambam. Most people refer to him as the Rambam, or Rabbi Moshe ben Nachman, the Rambam, right? And so on. So you want to include those names too. So what they did was they went to a Professor Havlin. I don't remember, I think it was Bar Ilan University, but I'm not sure. And for the names, he provided the appellations that are generally used in the rabbinic literature. Like sometimes there are appellations that are not used, may come up with an appellation, but he took the ones that he felt were fairly standard, that you'd find when you pick up any rabbinic literature, it's going to refer to the Rambam, and so on. And he provided the appellations, so you take the names and the appellations, and you also take the dates of birth and death of each of these rabbis from the encyclopedia, whatever the encyclopedia says, when they were born, when they died. So you take the dates of birth and death, and you put it in there, and you now do a compactness measure. Whatever this compactness measure is, it's a mathematical formula. There is a justification for it, which is totally irrelevant. In other words, here's the story. You come in with a compactness measure, which is going to sort of tell you an idea of how closely these names and appellations or names and dates are close together as ELSs. The smaller the compactness measure, the better it looks. The bigger it is, the worse it looks. But it doesn't tell you what the probability is, nor can you calculate and expect it from it. Okay? Now, supposing you pick the right compactness measure that really does measure how compact they are. Okay? Then the experiment may succeed, may not succeed. But if it's true, it has a better chance of success because you picked your compactness measure correctly. On the other hand, if you pick some compactness measure that makes no sense, then it's bound to fail, even if it's true, because you didn't measure it right. Sort of like trying to find some obscure star in the sky with a little telescope that you buy in a toy store rather than one of these big telescopes. It's there, but you're not going to see it because you're not using the right instrument to detect it. The same thing here. The compactness measure is the instrument for detecting it. We didn't measure it yet. The measurement comes afterward. So now this is an important thing, and that is that at this point there is a mathematical formula, and there's a justification of why we think this compactness measure probably should work. But what it is not relevant. What's relevant is when you do the test of what the probability is, did that succeed or not? Did you find the star or didn't you find the star? Was your telescope powerful enough to see it or not? Once you found it, you indicate exactly where it is. Other people can find it in the same place. You're all set. What brand of telescope you used is irrelevant. You used the wrong brand, you probably would never have found it to begin with. Okay? And you put in the book of Genesis to do this searching. So this is the basic structure of the experiment up to the point of calculating the probability. Everyone with me? Clear? Okay. This is what they found. And again, these are the compactness measure. You have a whole bunch of them for all the different pairs of dates and the names. On the left side, you see the most compact ones. Notice there are 19 of them that are very, very compact. And on the other end, there's only 2 that are very far away. Okay? What you see in the red bar, that's what you expect to find just by chance, if there's no real effect. Okay? Of course, you don't expect all of them to be exactly at the red line. Some will be a little bit above, some of them will be a little bit below, but that's going to be the average. It looks good. I'm emphasizing the point, it looks good. If it didn't look good, if it all looked like you expected, you probably know that the experiment failed. You don't even have to calculate the probability. But this is what you hope to find. Namely, there are more of them that are close together than you expect to find by chance. What you expect to find by chance is the red line. So, for example, there are 19 pairs of names and dates that are as close together as they can possibly be. There are only 2 that are as far apart as they can possibly be. Clearly, this does not look like random. Now, but the question is, okay, it's not totally random. It's not 50-50. Maybe it's only 1 in 10. Maybe it's 1 in 100. And the answer is, at this point, we don't know. It looks like we have a success, but we haven't proven that we have a success. Okay? So back here is the big structure. The next step is that they went to a peer-reviewed journal. Now, what's a peer-reviewed journal? A peer-reviewed journal is a mathematical or scientific journal where they publish scientific and mathematical facts, new things that have been found, and it's peer-reviewed. Peer review means that they're going to take several, usually 2 at least, sometimes more. In this case, it was 5 or 6 because it was so unusual. They're going to take several peer reviewers. These are people who have the mathematical or scientific background to evaluate it and see whether or not you've made any kind of a mistake. And presumably they are unrelated to the people who wrote the paper. They don't care one way or the other if the paper succeeds, doesn't succeed. They're looking at it purely mathematically. And in fact, the rules usually are that the peer reviewers do not know who the authors are, and the authors do not know who the peer reviewers are, so no one can influence anyone else. It's done in a completely double-blind way. And the first thing they said was, well, you have this list of names and dates. How do we know that was a priori? Right? They challenged it right away. They're not just accepting it. How do we know it was a priori? How do we know that you didn't take 3 columns of text, 2 columns of text, 5 columns of text? You did many, many experiments. You found, oh, this one works. Let's use this one. Well, it's not a priori anymore. You did a bunch of tests, in which case, if we don't know how many tests you did, we can't calculate the expectation. So what they said is, we want a new list, which we are going to specify so we know it's a priori. They specify take 1.5 to 3 columns of text instead of 3 and more. So it's a totally disjoint set of names, okay? And do the experiment again. The whole experiment, rerun the whole thing again with this, which is called list 2. Yeah.
It's not entirely disjointed though, right? You just have a larger set that includes the original set.
No, it doesn't. It's totally disjoint. It's between 1.5 and 3. but not 3 or more.
Oh, before it was 3 or more.
Before it was 3 or more, now it's 1.5 to 3. So it's totally disjoint. I think the data set size, if I remember correctly, I think was, again, depending on my faulty memory, but I believe it was 162.
So you're just narrowing the parameters here?
What?
You're like narrowing the scope?
No, you're not narrowing the scope.
Same
What you're doing is, it's the same experiment, but it's a new list of rabbis and with their dates of birth and death. Because we don't trust the set that you gave us before, that was the only set you tried. So we're going to give you a totally new set that you didn't expect us to do. And now we know it's a priori because we specified it. Now go ahead and do the experiment to get on this new list, and let's see if you get the same results. That's the idea. And so they did, and they did. Okay, I don't have the chart to show you, but it looks very similar to the chart that I just showed you. That was called list 1. This one over here is called list 2, and everything that was done since then is on list 2. Well, almost. You'll see the exception later. And now, the question was, but how do you calculate the probability? You have all these compactness measures. Now what do? One of the peer reviewers, his name was Percy Diaconis, that we found out afterward. He is a world-renowned statistician. And he proposed the way of calculating the probability, okay, which is something called the permutation test, which I'll show you in just a moment. It's different than the text randomization, which I showed you before. We'll discuss that in a moment too. Okay, what we're going to do is we're going to mix up the dates versus the personalities. So all the data is the same rabbis, the same appellations, the same dates, except that the information is wrong. The wrong date is connected with the wrong person, and so on. So that was done by the peer reviewer. He also set the criterion for success. It had to be 1 in 1,000 or less. The expectation. And in this case, it's all a priori, so the probability and the expectation turn out to be the same. He sets the criteria, and it was written into the paper. This is the criteria. They wrote the whole paper beforehand. They left blank the actual result. It was written and in print, not circulated, of course, not published, but among the peer reviewers and the journal, everything was put down, every single detail, how the compactness measure is done, personnel, everything, all written down with a blank by the result. And all that had to do before publication would be fill in the result. If the result is 1 in 1,000 or less, we publish. More than 1 in 1,000, we don't publish. We don't believe it. Now, why 1 in 1,000? The actual, if you look at scientific journals, what they usually require is 1 in 20, sometimes 1 in 100. You can check that out. It's easy to find out. Okay? But, you see, extraordinary claims require extraordinary proof. Right? If I tell you that I have a green tie at home, you probably believe me, because who cares? Right? It's an easy thing. Why would I lie about it, right? But if I tell you I saw a flying saucer, you're going to say you have a picture of it? Well, no, a picture's not enough. Where did it land? Let me go out and see it myself. You know, that kind of thing, right? You're going to require much more proof because it's an extraordinary claim. Well, this is an extraordinary claim, that there are these codes in the Torah that tell you when rabbis who wouldn't be born until the 9th century. Remember, the Torah was given 3,300 years ago. The entire world acknowledges that it's a minimum of 2,000 years old, because then it was translated into the Greek under Ptolemy II of Alexander. And therefore, you have a minimum 2,000-year-old document, detailed information about people who would live between the 9th and the 18th century. That was the encyclopedia. That's extraordinary, an extraordinary claim. For that, we did 1 in 1,000 before we believe it enough to publish it. Now, this is the permutation test. Here is the original data. Name set 1, date set 1, name set 2, date set 2, and so on. You pair each name and appellation with the date of birth and the date of death. And you calculate a compactness measure, which is on the top over there. That's the true score. What it means, no one knows. All you know is that the smaller it is, the better. But other than that, it has no significance. Now what you're going to do is you're going to start mixing them up. You're going to keep the names the same, but keep on mixing up the dates. And for each one, you're going to calculate. So you calculate this, and there's the score. You get a score of 0.001, which is not as good as the other one, because it's mixed up data. It's not real, right? And you do that 1,000,000 times. And for each one, you calculate a score. You keep on going and going and going until you do 1,000,000 times. Actually, you do 999,991. The real test, the true one, is the million. Okay? And you see, where does the real one rank in terms of how small it is among all the others? So, for example, here you have a whole bunch of numbers. The one second from the bottom, that ranks number 2. And therefore, the probability, see, now we're getting a probability. The probability would be 2 out of 1,000,000. I did 1,000,000 tests, it ranks number 2. The probability of getting rank number 2 or rank number 1, which would be even better, is going to be 2 out of 1,000,000. Okay, everyone with me? So you see, there's no mathematical calculations. He laughs. I mean, yes and no. I mean, there's no serious math over here. Just trying many different trials, right? If I tell you that a guy, he's so good with a gun that he's a 95% shot. 95% of the time when he shoots at something which is at 50 meters, he hits it. Okay? It's only 1 centimeter wide. You say, okay, make a little target 1 centimeter wide, you station it 50 meters away, and you say, go ahead and do it, 1,000 times. And sure enough, 95% of the time, approximately, he gets a hit. And it's true. That's what we're doing here. Exactly the same idea. But notice that it's an approximation. Because I said it was an average. Right? So what it does over here is going to be an approximation. The more tests you do, the more accurate it is. The problem is that the more tests you do, the more time it takes on the computer. So you're limited by what you're able to do.
How long does it take for the computer to do these calculations?
I'm sorry?
How long does it take for the computer to do these calculations?
So this calculation was actually done back in the 1980s, the late 1980s. And at that time, on the computers that were available in several schools, that the researchers were able to get access to their computers, I think it took something like 3 or 4 weeks of running at night when the school wasn't using the computer. For the entire night when no one was there, they were running it, I think, in 2 different places. And, by the way, let me just mention, for those of you who are interested in more details about this, or the talk that I gave last time, or the talks that I'll give in the future, it's all included in my book, The Cosmic Puzzle. It's available on Amazon. Unfortunately, the hardcover book sold out completely, 1,000 copies sold out, but it's now available in paperback. So if anyone wants to read it at their own pace and get into the details, and you can either miss the detail, skip the details which are in the endnotes, or just read it superficially, or read all the endnotes and get all the details, including more that I'm giving you here.
The endnotes include the formulas?
Yes, the endnotes include all the formulas, every detail. So that if someone wants to say exactly how did you do it, it's there. But it's in the endnote, not in the text, so that it doesn't bog people down who don't want to see that.
Have anybody tried to replicate that experiment nowadays?
I did back then, but we'll talk about what's happening nowadays later on. Okay. In fact, we're almost out of time, and we still have plenty to go. So, but thank God we do have time afterward. Right? There's not another class coming in, so we can go on.
It's probably class at 6:30, but you can technically
What?
go until then.
Oh, it's at 6:30.
Usually this one at
Okay,
6:30.
great. Okay. Now the actual ranking that was found was 4 out of 1,000,000. It ranked 4 out of 1,000,000. But remember before I told you that if you're going to do more than one test, you have to keep on multiplying the probabilities by the number of tests you're doing. In this case, they didn't know, to begin with, the very first experiment done, they didn't know which compactness measure was going to be the best. So they tried 4 different ones. Because of the fact they tried 4 different ones, they had to multiply the final probability by 4. So it ends up being 16 out of 1,000,000, which is 1 in 62,500. But the ranking was actually, for the best one of the 4, was 4 out of 1,000,000. By the way, that's 62 times stronger than the referees required, 1 in 1,000. So it passed the peer review by far. It was published, Winston, Rips, and Rosenberg, equidistant letter sequences in the book of Genesis in Statistical Science, August 1994.
And that's a lot higher than a regular null hypothesis.
Oh, for sure. Much, much higher. Yeah. Okay. So now we come to a question. We talked before about randomizing the text, mixing up the words within each sentence, but that's not what we did here. What we did over here was we permuted the dates and the names. That's different. The question is, number one, why? And number two, what's the difference between them? Okay? So, number one, two ways. Number one is produce many monkey texts by permuting the words within each verse, for example, and then rank the codes found in the true text with those found in the monkey texts. The second way, which is what we did for the Great Rabbi's experiment, is to permute the dates versus the names of the personalities. The question is, number one, why did they do it the way they did it? Number one. And number two, which one is better? So, if you use monkey text, the text, what we call text permutation, what is the hypothesis that it's testing? It's testing the hypothesis that the Torah has codes in it that other texts that are similar to the Torah do not have, which is exactly what we want to test. The permutation test says that the information, the correct information about the dates of birth and death of these rabbis is encoded better than the incorrect information, which is very similar, but it's not quite the same. Which is the hypothesis that we're really trying to test? It's number one, but we're doing number two instead. Question is, why? And the answer is, this one is better, it tests the hypothesis better, and as we'll see later, it works better, but the problem is that it's extremely time-consuming. And back in the 1980s, when this experiment was done, it was totally out of reach. Totally out of reach. You just couldn't do it. And that's why Diaconis suggested the permutation test instead, because it turns out that also looks like it's out of reach. And by the way, I also, when I was first told that this is what he suggested, I said, great, the guy is suggesting something that there's no way to do. And then they showed me that he found a very clever trick on how to do it very, very fast. But there is no such trick for the text permutation. Okay? So that's why it was done that way, and we're going to come, that's very important, because we're going to come back to this later. Okay, so here is the Great Rabbi's experiment as we just described it. And the question is, what do the critics claim? Okay? You see, what they're saying, and notice how the red is going down because it affects everything that comes after what they claimed. And that is, they're saying that Havlin, Professor Havlin, when he provided these appellations, he chose which appellations to use. There was no algorithm for that, right? He just chose whatever he thought was right. That's objective. And you know what? He could have cheated. He could have cheated by taking all the appellations for Rambam, there are probably others, right? And say, try each one and see, oh, this one works the best, let's use that. This one, oh, that worked the best, let's use that. Well, sometimes, and then introduce some others that you don't have a complete choice, because if you leave out Rambam, everyone's going to say, well, wait a minute, how'd you leave out Rambam? That's obvious. So you've got to be careful that it looks reasonable. Okay, you can justify all the changes. But if you claim that the appellations are not a priori, then everything that follows after with the compactness measure, the calculation of the probability, it's all not a priori. And if it's not a priori, we don't know what the probability is. That's the claim of the critics. Now, it turns out that they published that in the same journal, Statistical Science, in May of 1999, solving the Bible codes puzzle,
When was
which
the original
you
one
brought to
published?
my attention earlier today.
When was the original one published?
Sorry?
1994.
The original experiment, when was it published?
Yeah, that was published in August, I think it was August of
1994.
1994. So it's 5 years later. Okay, but you see, it's interesting. Statistical Science was trying to, they got a lot of flack for publishing that first paper. You know, you're trying to prove the Torah is real, you know, nowadays, who believes anything like that? They were very anxious to have a paper like this. But enough said about that. There's much more behind the scenes that's very unsavory, but I won't.
Do you explain in your book how that explains the permutation experiment?
Yes, it's all explained. It's all in the book, all the details. Except for the very, very latest details, the things that have just been done in 2022, that's not in there because the book was published 2 years ago. So that's not in there. But other than that, it's all in there. Okay, now they did something else. See, notice that if the expected is equal to the probability, remember, only if the appellations are a priori. In this case, the critics have claimed the appellations are not necessarily a priori. Now, they will say, we're not saying they're not a priori, we're just saying that we don't know if they're a priori or not, but that's enough. And if you don't know, you can't calculate the expectation. Even though the probability is small, if the number of trials is enormous, then it doesn't mean anything. You still can't calculate the expectation. And one of the things they do is, in the red at the bottom over there, they also show that it's possible to cheat. Namely, they go ahead and pick their own appellations and do the experiment in War and Peace, the Hebrew translation of War and Peace, and they get a result very similar to the Great Rabbi's experiment. Now, what they say, which is true but very misleading, they say, well, it's not true. They say, we did the same thing as Wisdom and Rips, and this is what we got in War and Peace. If there are codes in War and Peace, then what's the difference between, doesn't mean anything if it's in the Torah.
We don't know that was a priori.
They don't claim it's a priori.
Oh.
They say we cheated. They admit that we cheated. But what they're saying is if we could cheat, then the original researchers could have cheated too. And you know what? They're right. They're absolutely right. It's a big flaw in the original experiment. It's not necessarily a fatal flaw. Because you see now, very careful, listen. They proved that it is possible to cheat. They did not prove that they actually did cheat. There's a big difference between those two. The question is, but how are you going to prove they didn't cheat for an experiment that was done back in the 1980s and published in 1994? That's the problem. And I'll show you how I solved that problem. Okay? But they actually produced an experiment in War and Peace that looks very much like WRR. They say we did the same thing as Wisdom. They're implying that Wisdom cheated, and we cheated also. But it's not so. They cheated, and Wisdom might have cheated, but they haven't demonstrated that they actually did cheat. That's the difference. Okay. And their paper was published in Solving the Bible Codes Puzzle in Statistical Science, May 1999. So now we're going to go into the cities experiment and its implications in the controversy. This is an experiment that I did. I described it last time, but the Kitzur, short, what I did was I took exactly the same experiment that Wisdom and Rips did, the same names, the same appellations, the same compactness measure, the same calculation of the probability, everything identical, except for one thing. And that is, instead of using the dates of birth and death, I used the cities of birth and death, or sometimes called the communities of birth and death. That was the only change. Okay? So, names and appellation are taken from WRR, from Wisdom and Rips, and therefore they're necessarily a priori. There's no question anymore that now, for this experiment, not necessarily for his experiment, but for this experiment, it's definitely a priori because it's already been published. So I'm fixed. I can't change it anymore. I've taken exactly what was there before that everyone's seen. This is now a priori. So remember, something could be a priori now, even if it wasn't a priori then. So for Wisdom and Rips, the claim is it wasn't a priori, but over here you can't make such a claim. There's no question it was a priori. No one can deny it, and no one does deny it. Okay. Now, what about the cities? That's the new element. The question is, are the cities a priori? How do you know that the cities are a priori? And the answer is that it was done differently. Instead of consulting an expert like Kaplan, who has subjective choices each time, should I use this appellation, should I use that? Instead, we had an algorithm, which was published along with this paper, an algorithm that uses two encyclopedias, and it's Encyclopedia Hebraica and the same encyclopedia that they used with the great rabbis. And it tells you exactly what to do to get the city. In other words, look at the name and see what does it say he was born. If it doesn't say where he was born, look in the Encyclopedia Hebraica and see if it says there. Similarly with the date of death. Once you find the place where he was born and died, now you look up that entry in the Encyclopedia Hebraica to see how did they spell it. So everything is an algorithm, step by step by step by step. You can't deviate from the algorithm one bit, and that gives you the list of names and dates. So the question is not whether the cities are a priori. The question now is the algorithm a priori? And here's the trick. The trick is that when you choose each one, you have choice. You can make it work out the way you want it to. But when you have one rule, there's no way you're going to have one rule work for all 162 names. You know, you may make it work for some, but then it's going to work pretty bad for the others. And that can be demonstrated mathematically, but this is the idea. Okay? The probability, the compactness measure, the calculation of the probability, taken from WR, so that's all a priori, there's no question about it anymore. What I did, though, instead of using only list 2, I combined list 1 and list 2 in the experiment. We had a bigger data size and hopefully a stronger probability, which I did. Instead of 16 out of a million, I got 4 out of a million. 4 times stronger. And now another thing is that in the paper, I referenced the paper by the critics, by McKay et al., so that the peer reviewers are able to look and read their paper. There's a reference right there, and see what do they say, and see how does it compare with what I say. And I also referenced their website, which they have all their work also. So it's all in the paper explicitly. So there can be no question. Well, maybe the peer reviewers weren't aware of the controversy. No, they were very well aware because they gave them all the information. I didn't give it to them. I told them where to find the information as the critics put it in there. That's what I did. And this experiment was made public in the 1990s, even though it was not published until 2006. Now, these are 2 explicit conclusions that are in the paper, verbatim, copied over here. First is, it is highly likely that the list of appellations and spellings and the personalities was a priori for the Great Rabbi's experiment. 4, had the data been crafted specifically to produce compact configurations between ELSs of the appellations and ELSs of the dates, in other words, you were cheating, right? Then one would not expect the same personalities to form compact configurations with a totally new data set, namely the communities. That was in the paper, and the peer reviewers passed it. So they agreed. So in other words, the city's experiment is now 2 things. Number 1, it's a new experiment that succeeds, but it has a logical implication that says not only is this correct, but the original Great Rabbi's experiment is also correct. So we can now prove that even though Winston and Rips could have cheated, they actually did not cheat. Because if they had cheated, this experiment would not have worked. The second, it is important to note that although it is possible to manipulate the list of personality, appellations, and spellings in the Great Rabbi's experiment by not following a priori guidelines, so as to artificially obtain a small p-level, means probability, when the experiment is done on a text other than Genesis, it has never been demonstrated that it's possible to construct a linguistically correct protocol that will do the same. In other words, you can't fake the algorithm for the reason I gave you before. In the paper, it's more explicit. So that's 2 of the main conclusions of the paper. No one has ever shown, by the way, this was a challenge. You know, you were able to fake the Great Rabbi's experiment in War and Peace. You showed how you could pick all the different things. We challenge you, go ahead. If you don't believe in the city's experiment, go ahead. Fake the Great Cities experiment, the city's experiment. Go ahead and produce that in War and Peace with an algorithm, the same like we did. Go ahead and fake the algorithm. No one's been able to do it. The critics have not done that. Yes.
Are you concerned that with AI, someone could reverse engineer an algorithm that actually did manually choose it?
First of all, in the days when this was done, AI was in its infancy. That's number 1. Number 2, today, I don't know. I did use AI back before this, you know, where I worked, and in the military, you know, with the Defense Department. We did use artificial intelligence, but it was in its infancy at that time. We used, I don't know if you know about anything about AI, we used background, basically. You know, something like that would not be able to do anything like this. Today, I really am not up to date on AI, so I can't answer it. So in other words, the success of the city's experiment, which uses the same appellations as WR, proves that those appellations must have been a priori and that the Great Rabbi's experiment is valid. Now, how does McKay, the critics, published in 1999, whereas my experiment was made in the early 1990s, made public, how do they deal with the city's experiment? How can they claim that it was a fake if the city's experiment proves that it was not a fake? And what they say, and this is a quote, Gans uses the names of the cities of birth or death of the famous rabbis in place of the dates. it was later withdrawn, and they reference Gans 1998, which is a statement of mine on the internet, in which they claim I withdrew the experiment. I wrote an email to the editor of Statistical Science before this was published, but I saw the preprint, and I said to them, this is a false statement. Now, how do I know it's false? Because I'm Gans! Okay? I didn't get an answer from them. I wrote back again, and I said, please give me the courtesy of at least responding to me. So he said, I turned it over to another editor, and that was all I heard from them, and then they went ahead and published it anyway. Okay? Now, let's take a look at Gans 1998, posted on the internet, March 24th, 1998, and I quote, to date, I have not uncovered a single fact or even a hint that the list of cities that I was provided was manipulated in an attempt to make the results of the experiment appear significant, when in fact they are not significant. I have not uncovered a single fact that causes me to doubt that the conclusions drawn from the original cities experiment were accurate. This is what they're referencing, this document that's saying Gans withdrew his experiment. And they have the audacity in their paper on page 152, nothing we have chosen to admit tells a story contrary to the story here.
What?
Those are the critics.
Could you explain? I didn't quite understand what they're trying to claim that you said and what actually happened.
They claim that I did something which I never did, which I actually had a statement which says, I'm sure that everything is correct. I checked it out, there's no problem. They say, but you know what? He withdrew his experiment, which was a total falsehood.
Why did you take him to court? I mean, it's a big deal, though. You know, it's very misleading.
You know, I'll tell you something about the critics. They were very, very well funded. There were people who were willing to pay almost anything to disprove this experiment, the great rabbi's experiment. They had people traveling around the world. Some of them, I know, I came to give a lecture in London. The guy from the critics was there 2 weeks before me to explain why everything I'm going to say is false. They paid people to do this work. Okay? I'm not starting up with them. They won the war of PR. They didn't win the truth, but they did win the PR war. I tried to get Aish HaTorah to fund a whole response to them. Aish HaTorah didn't work. They wouldn't do it. They weren't willing to get involved. I don't have the personal resources to be able to fight that. I mean, we know who the one guy who was funding all this. We know there may be others, but there was one guy. He's a multi-millionaire.
Why would they fund this against you?
They don't want the Torah to be true.
Because they are atheists. They don't want you to prove that the Torah is true, that there's really a God. That's why. Okay, onward. Let's look. We saw one confirmation of the great rabbi's experiment, namely the city's experiment. Let's take a look at the most recent research. Okay, so here we have. This is the black. The black bar represents the entire Torah. The red part is the book of Genesis, Bereshit, right? This is where the experiment was done. Because in the time when they did the great rabbi's experiment, they only had Genesis on a computer, computable form. The rest of it wasn't done yet. And therefore they did it only on Genesis. So Genesis is 78,064 letters long, and Wisdom decided, I wonder whether or not the same effect is found in the next 78,064 letters. Now, a few things I want to point out. Number one is that this is the strongest test of any statistical result if you have the data to do it. And that is, you claim you have a statistical effect, give me a totally different data set and let's see if you find the same thing. So if I claim to you that every person who has diabetes has a particular gene defect, okay, and I do a sample size of 100, and sure enough, it turns out that a lot of them do, but not all of them, okay? And I try to get this published, the journal is probably going to say, well, 100 is really not enough for us. Why don't you go ahead and take another set of 100, or maybe better yet, 1,000, and let's see if the same effect is there. Then we start believing it, right? That's statistics. You have a result on one set of data, try it on another. Now, it's such an obvious idea that you would think that someone would have thought about it beforehand, right? And in fact, they did, sort of. And that is, you try it on Genesis, how about on Exodus? Now, 78,064 is much more than Exodus. Exodus is much smaller than Genesis, okay? You try it on Exodus, nothing. I tried it too, nothing. You don't see anything. So why would you do this? It takes a genius like Whitstone to realize there's something missing. So he tries this experiment, and lo and behold, it's there. Next 78,064 letters, with a probability less than 1 in 1,000, the same effect on a new data set that no one looked at before. The question is, why? Why did it fail on Exodus, and yet it succeeds over here? And this was the brilliance of Whitstone. I personally, I wish I had thought of it. I never did, but he thought of it. And that is that when you just try the next 78,064 letters by themselves, you're missing out on something. You're looking for the codes that are in those 78,000 letters. But what about the codes that span from one set to the other? You're missing all of those. It turns out that almost all of these new codes are between the two. Very few are in the next 78,000 letters. Biden's completely contained in there. And that raises the big question, and that is why? And that's one of the mysteries of the codes we don't know the answer. There are many mysteries, this is one of them. We don't know. We don't know why it's true, but that's what it is. That's what we observe. And that's what you can do, is observe, and maybe someday we'll have an explanation of how this is working. But it's there, and not only that, it was published. Badad is the peer-reviewed quarterly journal of Bar-Ilan University. They were very reluctant to publish this. As you might expect, after it being shot down in supposedly shot down in statistical science, they didn't want to get involved. But Jerome Whitstone challenged them. He said, are you honest or are you not honest? I'm giving you this experiment. You try to find a flaw in it. Do whatever you can. And if you can't find the flaw, then you go ahead and publish it. And if you find anything wrong with it, then don't publish it. But do the honest thing. Are you willing to do that? And they said yes. Now I'll tell you, they peer-reviewed it for more than a year. They had virtually every one of their peer reviewers go through this. But I'll tell you, there was one person who went through it before them, besides Whitstone. That was me. Okay? I have an inner sense. Which I don't understand. If I look at anything, some kind of mathematical computation, scientific thing, anything, if there's any kind of a logical flaw in it, or something missing, I sense it. Usually I understand why, but sometimes it's so deep, I don't even understand why, but I understand something is wrong. I know something is wrong here. And so, all the Whitstone and Rips, nowadays, when they're doing experiments, they want to think of publishing it, Rips came from Yerushalayim to Bet Shemesh, where I live, to consult with me, go through the experiment and see if I find the flaw, if I feel that there's something wrong. And it wasn't. There was one paper that we wanted to publish, and I felt there was something wrong. I gave it to a professor of mathematics. He said also he felt something was wrong. I could not find the flaw. But we did some control experiments. We showed that there was something wrong with the experiment. No one knew what. We didn't publish it. We didn't submit it for publication. It took 6 months of an entire team, including me, before we finally figured out what was wrong with it. It was that subtle. But I felt that there was something wrong with it to begin with. So I went through this stuff beforehand, and I knew they wouldn't find the flaw. I didn't know how I knew, but I knew. But proof is in the pudding. They could not find the flaw after over a year of peer reviewing it. It's published in Badad number 35 in 2020. Now, he then decides, how about if we switch, this as a control experiment, switch the order of Genesis and the 78,064 letters. Does the experiment still work? What do you think, yes or no? Why not?
It wouldn't make sense.
It's not the Torah.
Yeah.
Huh? Well, yeah, but you still find the same things in Genesis, the same things in the 78,064.
test.
What?
Now you're doing the monkey test.
Yeah.
Not yet. We are. We are.
But it's-
But remember what I said before?
It should be fine, 'cause it's still
The codes are
contained.
not in the 78,064 letters self-contained in there. They go between Genesis and the 78,064 letters.
In
So
order.
as soon as you switch the order,
It messes up all
you
the
destroy them all,
right.
and now you're not gonna find anything. It does not work. Beautiful control experiment, published also in the same paper, plus several other controls as well. But I'm not gonna get into them, they're a little bit more complex. Okay, so conclusion, WR passed the strongest and most definitive statistical test. Ask any statistician, you don't have to believe me. Go to any statistician, say what's the most direct and powerful test of any statistical result, okay? And he's gonna say, if you have enough data, obviously if you don't have enough data, then you can't do it. But if you have enough data, then that's the best possible test. Ask any statistician will tell you that. You don't have to believe me. By the way, very important, you apply the same test, this test, to the decay data, what they got on War and Peace, it fails completely. You don't get a significant probability. What that means is that now, instead of arguing about rabbinical appellations, and which are right and which are not right, we have a mathematical test that can differentiate between a fake and a real experiment. That's what this does. That's very important. I don't have to depend on any kind of subjective judgment anymore. I apply this test, it works or it doesn't work. Almost. In the sense that if it doesn't work, it doesn't prove that it's not right. But if it does work, it proves that it is. So that's important. A mathematical technique to differentiate between a fake and what's not a fake, what's real. I have to catch up on my notes over here because I'm doing this basically by heart. It works fine anyway. Okay, now permutation test versus the text permutation. The one that was done in WRR versus the text permutation. Which one is the better one to do? The text permutation, right? Unfortunately, we couldn't afford to do it back in the 1980s. But now we can. With faster computers, we can now do the text permutation. But we can't do 1 million. Even so, it's still very expensive. We can only do 50,000. So if you do the permutation test with 50,000 tests on